So today we will learn about image restoration. Okay. So what is the meaning of restoration? Definition. So restoration is process of restoring or retrieving the original image that has been degraded. Okay, that has been degraded by using prior knowledge of the degradation phenomenon. Degradation phenomenon means generally images may be affected. Okay, when will be images will be affected? While transmission it may be affected, right? While transmission image may be affected, right? While capturing also images may be affected. Okay, while capturing also images may be affected. So the effect due to capturing time is called degradation. So during transmission the image is affected is called noise. Okay, so the process of retrieving the original image that has been degraded by using the prior knowledge of degradation means we have to know about degradation, which type of degradation it is. Okay, means while capturing the effect may be many ways. Okay, those are degradation, noise. Okay, degradation and noise. So how we perform a restoration? Perform restoration. First in by removing degradation. Second one is by removing noise. Okay. So image restoration is nothing but process of restoring or retrieving original image that has been degraded. Okay, that has been degraded by using prior knowledge of degradation phenomenon. We must know about how images are degraded. Otherwise, we can't retrieve. So how can we perform restoration? By removing degradation, by removing noise. Okay. So what is degradation? What is degradation? Okay. So images are get affected or blurred during while capturing of images Okay, so there are several causes how images are degraded. What are the possible ways? The possible ways is first one is improper closing of improper opening and closing of camera shutter. Okay, means before camera ready, we make pictures, right? Immediately we take pictures. Okay, so that there may be blurred, right? That is one effect. Next, due to atmospheric conditions. Due to atmospheric conditions, we call it as atmospheric turbulence. Means suppose due to moisture or anything, the images may be blurred, right? So this is one type of degradation. Next, misfocus of lenses. Okay, misfocus of lenses. And one more is relative motion between camera and object. Okay, if camera is moving or object is moving, or both are moving at a time, they may be blur. Okay, they may be blur. So these are possible ways of degradation. Okay, these are possible ways of degradation. Okay, next, one more important topic is they will ask about differences between image enhancement and image restoration. Image enhancement and image restoration. So the basic differences are, first one is image enhancement is what? Quality improvement. Okay, quality improvement by modifying pixels, right? Image restoration means it removes the degradation. It is also one type of quality improvement only, because we remove the degradation. Quality improvement by removing degradation and noise. Okay. So restoring original image, by removing degradation and noise. So how it is analysis, we can say, how can we say the quality is improved? By subjective, means by rating. So the quality is good, bad, excellent, like this. By words, we say the quality of image enhancement. So in restoration, we analyze them. So it is objective type. We calculate mean square error, signal to noise ratio, etc. like this. So this is objective type. Next, third difference is it can be done in both spatial domain as well as frequency domain. Here also it can be done in both spatial and frequency domain. Here we no need of degradation function, noise estimation. Here we require degradation function and noise estimation. Okay. Any other techniques are here we are using filters, histogram models, etc. Okay. What are those filters? Sharpening filters, smoothing filters, etc. We are use. Here we use restoration filters like Wiener, least squares filters, Wiener filter, inverse filter, etc. So many. Okay. These are the basic 5 differences. Okay. Next. Basic image restoration or degradation model. Basic image restoration or degradation model. How it is looks. Okay. So to restore the image, we use restoration filters, right? Restoration filters. So that we get retrieved image, that is f cap of x comma y. Okay, x comma y. So this is original image f of x comma y. The original image is mainly affected with what? Degradation. So we have to find out degradation type. So it is represented with degradation function. Okay. And also I said while transmission, the image may be affected with noise also. Noise also. I am adding noise now. Okay. The combination of degradation and noise is called degraded image. This is degraded image. Okay. Degradation function is defined as H. Okay. That degraded image is given to restoration filter. Restoration filter. So then we get original image. This is restored image. Okay. Up to here we called it as degradation part. This is restoration part. Okay, restoration part. So in exam, if they ask only image degradation model, you have to draw this diagram completely and explain degradation function more detailedly, noise types more detailedly. Okay. If they ask image restoration model, then you have to draw this diagram completely and explain restoration filters also. You have to explain more about restoration filters also. Okay. So let us see the final equations for this one. Generally, we perform convolution operation. If the block is available means we perform convolution operation in time domain. Okay, in time domain. In frequency domain, it becomes multiplication. Okay, it becomes multiplication. So let us see the degraded image equation. Degraded image equation. G of x comma y in spatial domain. In spatial domain. g of x comma y is equal to what? For this image, we performing convolution h of x comma y. For that, we are adding noise x comma y. This is noise. Okay, so this is called degraded image. Now, a restored image is given as f cap of x comma y is the restoration filter. It may be considered, I am taking as R, notation R. The R is applying to degraded image. So g of x comma y convolution R of x comma y. Okay. What is g of x comma y? Degraded image. This is g of x comma y. So in frequency domain, capital G of u comma v is equal to capital F of u comma v. This convolution becomes product capital H of u comma v plus capital N of u comma v. Then f of u comma v is restored image is capital F of u, f cap of u comma v is capital G u comma v into R of u comma v. Okay, R of u comma v. These are the basic notations, equation notation, general notation, or simply we can write small g as h convolution f plus neta, capital G as h into f plus n, like this. Okay, simply without these notation x comma y. Okay, this is the basic image restoration model. Let us learn individually about different types of degradation functions, different types of noise, and different types of restoration filters. Okay, different types of degradation functions. Degradation functions. Okay, different types of degradation functions. So we already know about different types of degradations. What are those? Due to opening and shuttering of camera. Next, misfocus of lenses due to the movement of object and cameras. Like this, we learn about those things. So to estimate those functions, we have some degradation functions. We have to estimate those degradation functions. So it can be done in three ways. That is by observation, by experimentation, and by mathematical modeling. By mathematical modeling. So in observation, the degradation function h of u comma v is calculated for subimages. It is given as degraded image divided by original subimage. Okay, So here the observation, we calculate h of x comma v. Here we divide the sub images. Okay, we divide the sub images, image into sub images, and we estimate with this one using h of x comma u comma v is equal to g of u comma v by f of u comma v. Okay, next experimentation. Using experimentation, h of u comma v is given as degraded image with one amplification factor. This amplification factor is called strength of impulse. Strength of impulse means how we calculate A. Generally, what is meaning of experiment? For same circuit, we take multiple readings, right? Whether we getting correct output or not for every input, right? Same thing here, the original image camera setup. We have original image camera setup. For that camera setup, we take multiple images. And for that multiple images, we calculate this strength of this impulse. Okay, we calculate the strength of the impulse. So from that we can define the degradation function as g of u comma v by a. And mathematical modeling, h of u comma v is equal to e power minus k u square plus v square 5 power 6 whole power 5 power 6 5 by 6. Okay, where k is atmospheric turbulence. Okay, atmospheric turbulence. So these are the basic three types of estimation of degradation functions. Okay, next noise. Noise is unknown signal, right? Noise is unknown signal. So these noise can be estimated using, these noise are represented using random variables. Okay, random variable. So we have, for images, we have so many types of noise. In that, first one is salt and pepper noise. Salt and pepper noise, also known as impulse noise. Impulse noise. And second noise is gamma noise. Gamma noise or Erlang noise. These two are very important in images. And next important is Gaussian noise. Next, uniform noise. Next, exponential noise. Next one is Rayleigh noise. So these are all mostly random variables only. You learn Gaussian, uniform, exponential, right? Rayleigh. Now you will learn about salt and pepper and Gaussian or Erlang noise. So what are those? Okay. First one is salt and pepper noise. How salt and pepper noise looks? How salt and pepper will look? Salt will look as white granules, right? Granules, and pepper will look like black granules, right? Means like this dots. White dots are called salt, black dots are called pepper, right? So in image, if they available like this of dots, we called it as salt and pepper noise. Salt and pepper noise. The salt and pepper noise function is defined as probability function. P of Z is equal to PA, PB, 0 for otherwise. For Z is equal to A, for Z is equal to B. Okay. How graphically we represent like this. This is Z, this is P of Z. This is A, this is B. PA, PB. Okay. So in image, it looks like some dots, white and black dots. Okay, white and black dots. Then we call it as salt and pepper noise. Second important noise is Erlang noise or gamma noise. Gamma noise or Erlang noise. Salt and pepper are impulse noise. So it is defined as P of Z is equal to A power B into Z power B minus 1 divided by B minus 1 factorial for Z greater than 0, 0 for Z less than 0. Okay. The graph is available like this. Z P of Z. Okay. This is gamma noise. Because the noise are represented in random variable form. So we represent simply in random notation, random variable notation. So after that, Gaussian noise. So Gaussian noise is given as P of Z is equal to 1 by 2 pi variance into e power minus Z minus Z bar whole square by 2 sigma square. Okay, 2 sigma square. The graph is available like this. Okay, Z P of Z. This is Z bar. This one is B minus 1 by A. Next, fourth one is exponential. Exponential. So exponential is given as P of Z is equal to A into e power minus AZ for Z greater than or equal to 0 for Z less than 0. The graph is available like this. This is Z, P of Z. Next, fifth one is uniform. Uniform is P of Z is equal to 1 by B by A 0. For others. So the graph is looks like this. A, B. 1 by B minus A. P of Z, Z. Okay. And last one is Rayleigh noise. Rayleigh noise. It is given as P of Z is equal to 2 power B Z minus A e power minus Z minus whole square by B. Okay. The graph is given as like this. This is Z. This is P of Z. Out of 6, at least write 4 for exam. 4 for exam. In that, salt and pepper, gamma must and should. Gamma must and should. Must. Okay. For example. So whenever they ask degradation model, you have to draw that block diagram and you have to explain up to here. Okay. Up to here. If they ask restoration model, you have to explain about restoration filters also. Restoration filters also. So the restoration filters are classified into 2 types. Okay. The restoration filters are classified into 2 types. Restoration filters. Okay. Image contains only noise, contains degradation also, contains degradation also. Okay. So to remove this, we have 3 types of filters. Mean filters, order statistic filter, adaptive filters. Okay. And degradation means it is classified into again 2 types. Deterministic, stochastic. Deterministic means we have some knowledge about degradation. Stochastic means we don't have knowledge on degradation. Okay. Here we have linear, non-linear. Okay. In linear we have inverse filter, Wiener filter, constrained least square filter, and non-linear we have interactive restoration. Okay, interactive restoration. Okay, so whenever they ask restoration model, you have to explain this classification also. Individual terms your wish, but try to draw this classification also. Okay, now let us learn individually about these filters. Okay, mean filters. Just you have to remember the formulas only. Mean filters. So mean filters are classified into four types. Okay, mean filters are classified into four types. First one is arithmetic mean filter. Okay, arithmetic mean filter. So the restored image is given as f cap is equal to 1 by mn sigma gs of t, sigma g. Okay, where mn is total number of pixels. Okay, total number of pixels, sigma of. This is arithmetic mean filter. Next, geometric mean filter. Geometric mean filter, f cap is given as pi of g, pi of g whole power 1 by mn. That is geometric mean filter. Next, harmonic mean filter. Harmonic mean filter. So f cap of mn by sigma 1 by g. Sigma 1 by g. Okay. And one more is contraharmonic. Contraharmonic mean filter. It is given as sigma g power q plus 1 divided by sigma g power q. Okay, this is contraharmonic filter, where q is order of the filter. Order of the filter. When q is equal to 0, it is AM filter, arithmetic mean filter. Okay, arithmetic mean filter. When q is equal to -1, it is harmonic mean filter. Okay, harmonic mean filter. Next, order static filter. Order statistic filters. Order statistic filters. In order statistic filters, we have first one is median filter. Median filter. So f cap is given as median of g. Next, min and max filter. Min and max filter. So f cap is given as min of g. F cap is given as max of G. Okay, this is min and max filter. Next, midpoint filter. Midpoint filter is given as f cap is equal to min filter plus max filter divided by 2. Min filter of plus max filter divided by 2. Okay. Next one is alpha trimmed mean filter. F cap is equal to 1 by mn minus d into sigma g. Okay, sigma g, where d is 0 to mn minus 1. And next filter is adaptive filter. Adaptive filter. So adaptive filters are classified given as f cap of x comma y is equal to g of x comma y minus g minus ml. So this is adaptive filter. And other filters, other filters means when noise is periodic. When noise is periodic. The filters are classified as band reject, band pass, notch filter. Okay, these are the 3 types of periodic filters. So bandwidth reject filter function is defined as h of u comma v is 0 and 1. 0 for given band d naught minus w by t, d naught plus w plus 2 for others. Band pass is reverse of this one. H of u comma v is equal to 1 for d naught minus less than or equal to 0 for others. Notch filter is given as predefined neighbor set. Predefined neighbor set. We define the notch filter. So h of u comma v is equal to pi of hk of u comma v into h minus k of u comma v. Okay, k is equal to 1 to 3. Okay, these are other filters when noise is periodic. Non-periodic, periodic. In periodic, we have band pass, band reject. Third one is notch filter. Okay.